Welcome to the Udemy course on ROS for Beginners, Part 2 on Localization, Navigation, and SNAP. My name is Anis, and I will be your instructor throughout this course. The course is designed to introduce you to the world of mobile robot navigation. If you are struggling with learning robot navigation and you want to master and be proficient in navigation with ROS, then this course is designed for you. In fact, localization, navigation, and SNAM are the fundamental concepts in robotics. However, they are very challenging to learn, considering the steep learning curve and the plurality of interrelated topics, which makes it difficult to know from where to start and where to go. This course addresses this gap and follows a practical approach to introduce new learners to mobile robot navigation foundations and how it is implemented in ROS. The course is designed to introduce you to the world of mobile robot navigation in a quick and effective manner. The course follows a practical approach while also covering the theoretical foundation of these concepts and link them together. The course starts with providing the theoretical concepts related to localization in two-dimensional and three-dimensional spaces, which are essential to know for robot navigation. Then it presents the TF package, which is a very important package in ROS for robot navigation. Without a good understanding of the TF package, it is hard to understand how navigation is performed in ROS. Although there are TF tutorials on ROS Wiki and other documentation websites, TF package heavily relies on important theoretical concepts not presented in ROS tutorials. This course provides a systematic introduction to the necessary theoretical background and complement with demonstrations and programming activities of the TF package utilities and API. Then I present map-based navigation concepts in ROS. I first demonstrate how to build a map in ROS and explain in details all the configuration parameters of the SLAM algorithms to obtain a high-quality map. Then I present how to perform robot navigation using the map constructed with the SLAM algorithm in ROS. The experimental demonstrations are performed using Turtlebot 3 Simulator, which is the most popular robot simulator and platform used for teaching and education. This course assumes that you have some background on the main concepts of robot operating system, such as ROS nodes, ROS topics, ROS services, and an understanding of the basic notion of motion with ROS. If you do not have these skills, then I would recommend to first enroll to my course ROS for Beginners, Basics, Motion, and OpenCV to get all the necessary background. Welcome to the course. I am Professor Anis Kuba, and I'm glad to be your instructor in this course about Robot Operating System Part 2, Localization, Navigation, and SLAM. I'm currently working as a full professor in computer science in Prince Sultan University in Saudi Arabia. I'm also the director of R&D department in Gaytech Robotics in China, and also a senior researcher in the Sister Research Center in Portugal. I have been working in a lot of projects in both university and industry. I'm also the director of the Robotics and Internet of Things Lab, where I conduct a lot of research about the integration of robots into the Internet of Things and into the cloud. I'm also an ACM Distinguished Speaker and a senior fellow of the Higher Education Academy in the UK. To learn more about my biography, you can refer to my webpage. I have been also teaching robotics and drones for several years at the university, and I have written a lot of tutorials and developed several courses for ROS and robotics. I have also conducted training program certificates for robot operating system, which has attracted a lot of audience and contributed to promoting the learning of ROS. I'm glad to put my experience at the hand of students worldwide to teach them about robot navigation with ROS. this section, I'm going to introduce you to the Turtlebot 3 robot in a simulation mode, but also you can do the same thing in a real robot if you have already the hardware. I'm going to show you the different steps on how to install Turtlebot 3 robot in simulation environment, and also what are the different simulation options available for you to work with Turtlebot 3. And then I'm going to show you a small demonstration about these different environments. So I have here provided to you a simple guide to install Turtlebot 3. Of course, you can find the same instruction in the official website of Turtlebot 3 on Robotis website. But here I made just a summary because this information is actually spread in different pages, and sometimes it is confusing to install the Turtlebot 3 simulator. So I put everything here in one place in the right sequence order, so you can just follow and try to apply on your computer, and it should run and execute out of the box. So before installing Turtlebot 3, make sure to execute these two commands. First, you have to execute sudo apt-get update, and then sudo apt-get upgrade. So make sure to make also the upgrade, because the installation may fail if you don't do an upgrade in some cases. Then you can install the Turtlebot 3 package from GitHub. So first you need to go to the Catkin Workspace /src folder, and then you have to download these two repositories from GitHub using git clone, and then you provide the following link. And then do not forget to put -b Noetic devel if you are installing on ROS Noetic. And you can change Noetic by Melodic if you work on Melodic, or Kinetic if you work on Kinetic, but I do recommend that you do all your installation on ROS Noetic, which is the latest version. So you install the first repository, Turtlebot 3_msgs. This will install the messages of Turtlebot 3. And then you install the core Turtlebot 3 package. And again, you have to specify the branch here. It's Noetic/devel. And then you go to the Catkin Workspace and you do a Catkin make in order to compile everything. If you do so, you already installed all the core packages of Turtlebot 3, and this will allow you to run Turtlebot 3, but not the simulator. Now, if you want to do for the simulator, you have to do just a few steps more. After the correct compilation of the Catkin Workspace, you can download the installation of the simulation packages. Okay, so you go to, again, to source folder in the Catkin Workspace, and then using git clone, and then you provide the link to the repository of Turtlebot 3 simulator, this one, and then you go to cd Catkin Workspace, and then you do Catkin make. And as such, you will be installing the Turtlebot 3 simulator. Of course, it has to be done in this order. If you try to install the simulator without installing Turtlebot 3 core packages or Turtlebot 3 message packages, in this case you will fail, and you will have compilation errors. Then just after this, you can make the modification in the .bash rc file as follows. Okay, so you can go to the home directory and then write gedit.bash rc. So a good practice that I actually do, there are a lot of ROS launch commands for Turtlebot 3 simulator. There is the ROS launch for Turtlebot 3 fake, for teleoperation, for the empty world, for the maze, for also the house world. So sometimes it's maybe difficult to remember all of this. In my case, actually, I do some aliases like this. Okay, so for example, I do an alias burger, just for example, if I want to use the burger version of Turtlebot 3, because there are two versions, burger and waffle. Burger is the smallest one, and waffle is the most comprehensive. And for this, if you want to use burger, you need to type export Turtlebot 3_model equal to burger. And if you want to use waffle, you need to type export Turtlebot 3_waffle. So I put this in the .bash rc file as an alias to burger and waffle. It will execute these two commands, and that will be much easier. And also, for example, you can use, I use the alias tb3 fake to launch the Turtlebot 3 fake robot using the command ROS launch Turtlebot 3_fake, Turtlebot 3_fake.launch. I use the alias tb3 teleop ROS launch Turtlebot 3 teleop, Turtlebot 3 teleop key.launch. And also for opening in the maze world, in the house world. Okay, this is optional if you want to do the same thing. These aliases, I found them very practical, and I can access all these different commands just by typing fewer letters. And if you want just to type the whole ROS launch command, you can just type it without doing these aliases. But what is important and necessary is that at the end of the .bash rc file, you need, of course, to source the /alt/ros/noetic setup.bash to activate the installation workspace, and you have also to source your Catkin workspace to activate it. And then you can do export Turtlebot 3 model equal to Waffle if you want by default when you open a terminal, if you want to use a Waffle version. And you can change this one by Burger if you want to choose by default a Burger version when you open a terminal. So this will allow you not to type every time export Turtlebot 3 model equal to Waffle or a Burger, but it's going to execute automatically whenever you start any terminal. And at the end, you need to export svga underscore vgpu10 equal to 0, and this command will let to open Gazebo on a virtual machine and avoid crashing its display. If you don't put this, very likely Gazebo is not going to open if you use a virtual machine like I'm doing. So this one, if you look into the different forums, they will suggest to you to use this export instruction for Gazebo to open properly on the virtual machine. And that's pretty much it. Now, if you want just to use Waffle, put this export instruction, and if you want to use Burger, you can just put this instruction. But since you have already put in the .bash RC, you don't need to write it manually every time, at least for the version that you have put here. Having completed these instructions, you will successfully install the Turtlebot 3 simulator. And now let me take you through the different simulation environments that you can work in Turtlebot 3 simulator. So after installing Turtlebot 3, you can run it in simulation on different environments. So for example, you can run Turtlebot 3 in an empty environment, just an open space, like the case of TurtleSim, using the command roslaunch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore empty underscore world.launch. So this will allow you to open TurtleSim 3 in an open space. And this is like a straightforward application of the motion lectures that we have done in TurtleSim. So you can do the same thing, try to do the same thing as we did with TurtleSim, just by sending velocity commands in an open space to Turtlebot 3 robot instead of the TurtleSim robot. And if you have the real hardware, you can also try it on the real robot instead of the simulation, because the same code of the simulation should also run in the same way on the real robot. Okay, so this is the first environment. You can try it, you can make teleoperation using a teleop node that I'm going to show, or also you can develop the same motion applications that we have developed for the TurtleSim simulator. Okay, if you want just to play with this robot in the open space, you can also run the instruction roslaunch Turtlebot 3 underscore teleop, Turtlebot 3 underscore teleop underscore key dot launch. It will run the teleop node, and then you can do the same thing as you did with TurtleSim. You can play around with this turtle in this open space. And of course, you can develop your own Python script or C++ code in order to make it move by sending velocity messages using the twist message structure. Another also environment for the Turtlebot 3 is I call this as the maze environment. Okay, and you can run it using roslaunch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore war.launch. You will have this one. We are going to use this when we, in the lecture of the laser scanner. So we will make some exercises on how to make the robot move without hitting these obstacles. So you can see here we don't have a completely open space. We have obstacles here that are shown in black, in green, and also some obstacles in the middle in the white color. So one of the exercises that we will do later in the laser scanner lecture is to make the robot move here around without hitting any of these obstacles. So you will learn this afterwards. Another nice environment also is the house environment that you can open using roslaunch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore house.launch. Here you have a more structured environment with different walls, with rooms, and you have a table here, you have doors. So here we're going to use this more when in the second course, in the SLAM and navigation course, you are going to learn how to build a map of this environment and how to make the robot navigate autonomously in such an environment. For example, going from this room to this room without hitting obstacles by planning a path and going through this path in a smooth manner. A very important tool is RVs, and RVs is used to make different kind of visualization. It's the ROS visualization tool. And there is a version for Turtlebot 3, which you can execute using roslaunch Turtlebot 3 underscore gazebo, Turtlebot 3 underscore gazebo underscore rvs.launch. And here you can see, for example, one of the utilities of using RVs is to show the laser scanner. So you can see, for example, in this environment, and the robot is looking like this, there are obstacles. You can visualize them using the laser scanner data feed. Okay, like here, all these red dots represent the obstacles around the robots. And of course, you will learn in the laser scanner how to manage these kind of obstacles and how to avoid them while moving. You can also see the camera, so you can develop some computer vision application if you want. This is we are going to see this in more details with the OpenCV section. And here you can see more information about the topics available and different type of data that you can visualize in this tool. In addition, the TurtleBot 3 simulator offers a way to learn how to build a map for a particular environment. And for this, for example, you can run ROS-Launch TurtleBot 3 SLAM, TurtleBot 3 SLAM.launch, SLAM method, and here you can use GMapping or cartographer. There are different type of SLAM algorithms, and this is going to be discussed in details in the second course, ROS for Beginners 2, Navigation and SLAM. And also you can run the teleop key, ROS-Launch TurtleBot 3 teleop, TurtleBot 3 teleop key.launch, and then you can make the robot move, and while the robot is moving, is going to learn about the map of the environment and build it and save it as an image file and also as a metadata file in the YAML format. So these are the most important environments and capabilities of the TurtleBot 3 simulator, and we will be using TurtleBot 3 in the next sections related to OpenCV for computer vision, object detection for deep learning, and also the laser scanner. Okay, let's now make a simple demonstration to start TurtleBot 3 simulator. So I'm going now to start the TurtleBot 3 simulator in the world environment, in the maze environment. So this is the command, ROS-Launch TurtleBot 3 underscore gazebo, TurtleBot 3 underscore world.launch. So it will take a little bit of time to open. Okay, now it has opened, and we can see now the TurtleBot 3. So this is the waffle version. Okay, you can zoom in, you can zoom out. Okay, and in the same way, we are going also to start the RVs using the command ROS-Launch TurtleBot 3 underscore gazebo, TurtleBot 3 underscore gazebo underscore RVs.launch. Okay, and let's wait a little bit. So now we have RVs is open, and you can see here the TurtleBot 3. We can see the red dots, which represent the feed of the laser scanner. We can actually try to improve the visualization by improving the thickness of the points. So we're going to put this at 0.04. So you can see these are the obstacles in the middle, and these are the obstacles that represent the wall in the perimeter of the environment, which corresponds to this environment over here. Okay, and then we can also open the teleop node to make the robot move using the TurtleBot 3 teleop, TurtleBot 3 teleop underscore key.launch. Okay, and this is the node. So we need to use W, A, S, D, and X to move the robot. I'm going now to move the robot forward by pressing on W. So you can see that the robot is moving forward. And I press on W, I will press on S. The robot is going to stop. You can see also the robot moving on RVs. I'm going now to make the robot move forward. I need to activate this terminal. So now I'm pressing on W, as you can see, and the robot is moving forward. So you can visualize this in RVs, or you can visualize this in gazebo. I will stop the robot now. I will make the robot rotate using the A key. Okay, you will see the robot rotating. And you can see also the laser scanner feed is going to be updated, okay, when the robot is moving or rotating. Okay, so this is just to get started with TurtleBot 3. Of course, like any other robot, you can do ROS node list. And these are the list of nodes that are running. Okay, so the robot node is called Gazebo here. And you have the Gazebo GUI. You can make ROS topic list to see the list of topics. Okay, and here we have the scan topic. We discussed this in more detail in the laser scanner lecture, and you can see the different other topics available over here. Okay, this was just a very quick and brief overview about Turtlebot 3, which we are going to use in the next lectures with OpenCV and also with laser scanners. In this video, I will show you how to get the code needed in this course from GIT Hub. First, you need to go to the source folder of your Catkin workspace using the command cd catkin src. Then, open a web browser and go to the GIT Hub repository on my account at the address www.github.com/aniskuba/ROSCourse2. Copy the link of the GIT Hub repository project of this course. Go back to the command line terminal and drag the command inside the source folder of the Catkin workspace, git clone, and then paste the address of the repository that you copied. Press enter and wait until the package is downloaded. Go back to the Catkin workspace folder and execute the command catkin main to compile the whole workspace with the new added repository. Note that you must make sure that you have Turtlebot 3 simulator already installed for the compilation to work. Then use any editor like Sublime Editor and open the source folder of the Catkin workspace, and you will find the newly added package that contains the code needed for this course. Robot navigation is a very complex problem and requires the knowledge of different disciplines such as linear algebra, geometry, trigonometry, physics, mechanics, etc. However, ROS makes it very simple for us to make a robot navigate in space. In this course, I will provide both the theoretical foundation of navigation in addition how it is implemented and how it works in ROS. Several online tutorials on ROS directly jumps into the ROS concepts without explanation of the theoretical foundations, which are very important to know. On the other hand, several robotics courses focus on the theoretical foundation of navigation, but without linking it to ROS navigation stack. In this course, we will combine both approaches. I first start with presenting some basic theory in an intuitive manner. Then I will illustrate this using ROS. Before going into the theory, I would like to give you some intuitions through an introductory navigation demo on ROS. This demo will introduce you a few general concepts that later we will cover in more depth theoretically. Then we illustrate how it works in ROS through several examples. This is the general strategy of the course. Let's get started with our first demo example. In this demo, we will use Turtlebot 3 simulator. You can download and install the Turtlebot 3 simulator from Robotis website if you did not install it earlier. You can simply do that by going to the website at this link to install the core packages of Turtlebot 3, and then go to the simulator page on this link. Then follow the steps for the installation to install the simulator package. Once this is done, you can perform some simulations using Turtlebot 3. You can also use my virtual machine, which contains all the packages pre-installed. First, we start the simulation environment of Turtlebot 3 using the command launch turtlebot 3 gazebo turtlebot 3 _ house.launch. And here you can find the simulation environment of Turtlebot 3 inside the house. In this demo, I will just let you make a few observations that will help you understand later the need for the theoretical concept that I will present in the next section. First, in the RV's navigation interface that you can see on the right side, we first need to tell the robot its exact location in space, because when it starts, it does not know where it is located. So you can observe that the real position of the robot in the environment is located in this place. However, in the RVs, it is located in a different place. And you can see there is also a deviation of the laser scan readings. So we need actually to put the robot in the same position as it is in the real map in the environment. We can do that using the 2D pose estimate, which allows to place the robot manually in its correct physical location that we can see in the simulator, or in the real world if we work with a real Turtlebot 3 robot. So here we have 2D pose estimate, and then I will try to put the robot in the same location. We need also to specify the orientation of the robot. And you can see now the position of the robot is more accurate, and you can see even the laser scan match exactly the location of the walls that the robot is able to detect. Now the question, what is the location and orientation of the robot? We can obtain this information like any other in ROS through the ROS topic. Let us do a ROS topic list and find the list of topics. ROS topic list. And here we can visualize the list of all topics. Now we want to identify what is the topic that represents the location of the robot. Before doing that, observe that the environment is represented inside a grid where each square is 1 unit of distance in the x-axis and in the y-axis. So here in RVs we can enable or disable the grid, and it is shown over here. The middle point of the grid is the point 0, 0, and it is its origin. We will understand this in later lectures with more details, but just consider that the origin is in the middle. The location will be made with reference to this point. So at this point, we have the intersection of the x-axis and of the y-axis at this point. We call this a reference frame that we use as a reference to determine the location of the robot. We can visualize this frame on RVs using the TF topics, which show us all the frames. So we can go to add. Going down here, we can add a TF topic, and we will understand later what is TF. It means transformation. And then here we can visualize the different frames. So if we zoom in, we can visualize different frames. We can also observe in global option the list of available frames, as you can see here. These are the different frames available, and we choose one of them as a fixed frame. One frame is used as a fixed frame to visualize the location. and is typically the map frame that represents the global locations in the map. For the moment, just have in mind that a frame is a reference that allows to localize an object with respect to it. We will revisit this concept later theoretically in the next sections. Let us visualize all the frames as you can see here. We can observe the map frame, the ODOM frame, and also several other frames attached to the robot. These frames are very important, and we will understand the relation between them in the next section. Observe that the map frame and the ODOM frames are shifted a little bit. We will see the implication of this shift on the location now. So you can see that the map frame is exactly located at the center point 0, 0, and the ODOM frame is a little bit shifted from the map frame. We will see later how each frame is used to localize the robot. In the list of all topics, we can find the topic ODOM, which refers to the pose based on the odometry information. Let us see the content of this topic using the ROS topic echo ODOM. ROS topic echo /ODOM. We can observe that the location of the robot using the ODOM topic is -2.99 and 1.00. This is the position of the robot with respect to the ODOM frame. So remember that we have visualized the ODOM frame. It is this frame located here. And the position with respect to this frame is -299 and 1.00. In the list of topics again, using the ROS topic list, we can find another topic used for the localization of the robot and is called AMCL pose. This location is related to the global location of the map and not with respect to the odometry. So it is important to know that a robot can have different types of locations depending on the reference frame used to localize it. So what is the value of the AMCL pose location? In this case, we use ROS topic echo AMCL pose. And here we can find that the location is equal -3.01 and 1.01, which is a bit different from the ODOM position. We notice that this location is related to the map frame. And remember that the map frame and the ODOM frame are slightly shifted, which is the reason why the two locations are different for the same position of the robot on the map. Again, the frame plays an important role to tell about the location of the robot. We will analyze this deeply in the next lecture. Just remember that the map frame is the global frame that refers to the global position on the map. And we have also the orientation here. We observe that the orientation is represented by 4 strange values, X, Y, Z, and W. As human beings, these values do not make any sense related to orientation for us. In fact, this is a special representation of the orientation that is called quaternion, which is used by default in ROS to encode the orientation. As human, we understand rotation angles like yaw, pitch, and roll. In the next lecture, we will introduce the theoretical foundation of orientation in 3D space, and we will see the relation between the human readable format of the orientation, roll, pitch, and yaw, and the ROS readable format of orientation called the quaternion. And you will understand why quaternion is the preferred format for representing orientations in ROS. We need to send a goal location to the robot, and the navigation stack will make the robot navigate to it while avoiding obstacles. Observe here that we have 2 types of planner. We have a global planner and we have a local planner. So when we send, we can use the 2D nav goal button in order to define a goal location for the robot. For example, I want the robot to move to this location. And you can see that the robot first plans a static obstacle-free path, which we call the global path planning, and then executes the path using its local path planner. which also avoids dynamic obstacles. In this course, you will learn all the details about the global path planners and local path planners, and you will understand how to tune their parameters for better and smoother navigation performance. In fact, the navigation stack has a lot of parameters, and it is important to know them all to be able to take advantage of it. The bad configuration of the navigation parameters may lead to very low navigation performance and poor obstacle avoidance. In addition, you will learn how to build your own map and use it for navigation. As for now, we made enough introduction to the challenges and main concepts that we will cover in this course. It's time to go for the details and understand every concept very well for an ultimate excellent navigation performance. Welcome to the first section in this course about frames. Imagine that you have a robot in space. The first thing you think about is how to express the location and position of this robot. Indeed, this is the most fundamental question for robot localization and navigation. To designate the position of a robot in space, we first need to specify a reference that will be used as a coordinate frame where the position is represented. In this section, we will introduce the concept of frames. At the end of this section, you will be able to recognize the concept of pose and coordinate frames, and also to represent the position and orientation of the robot in space. So let's get started. In this lecture, we introduce the concept of frames and the pose of a robot in a frame. Imagine that you have a robot in space like in this picture. The robot is located at a certain position and it looks at certain orientation or direction. The combination of a physical location and orientation is called a pose. So, the pose is the location plus the orientation of the robot in space. This is the first thing you need to know. But now, if we ask you the question, what is the location and orientation of this robot? It seems that it is difficult to answer this question because we do not have any reference. Thus, without what we call a coordinate frame, which means a reference to express the pose, we cannot determine the position or orientation of the robot or an object more generally. Let us consider the following coordinate frame. This is a coordinate frame in two-dimensional space because it has only two axes, the x-axis and the y-axis. It has a horizontal axis called the x-axis and a vertical axis called the y-axis. It is now clear that if we ask the question, what is the position of the robot, we can answer it now as the location is 8 at the x-axis and 5 at the y-axis. It is also possible to express the orientation of the robot, which is the angle made between the horizontal axis x and also the line specifying the direction of the robot. In this case, it is 45 degrees. In summary, we have a coordinate frame that is called W or FW, in which the position of the robot is 8 in the x-axis and 5 in the y-axis, and its orientation is 45 degrees. So x is equal to 8, y is equal to 5, and theta, which is the angle, is equal to 45 degrees. The pose of the robot is expressed with the tuple 8, 5, and 45. So now you understand what is the pose of the robot in two-dimensional space. For example, if we have a robot navigating inside a map, as shown in this figure, the pose of the robot is 7 for x, 3 for y, and theta equal to 0. Now, imagine that we have another reference coordinate frame that is translated with respect to w. So here we have fw and we have fw1, and you can see that there is a shift between both. what will be the robot position with respect to the frame W1. Not only translation, we can also have a rotation. Imagine that I have another frame that is called FW2, and I would like to specify what is the position of the robot inside the frame W2. It is also possible to have the same question for a rotated frame W2, as you can see in this picture. Will the robot have the same pose in W2? Of course not. So now the question is how to determine the pose of the robot in the new coordinate frame W1 or W2. For this purpose, we need to understand the concept of frame transformation, which we explain in the next lecture. In the previous lecture, you have learned how to express the position and orientation of a robot in a two-dimensional frame, which represents a fixed reference. This fixed reference is used to localize the robot in space. However, in real world, there is no single reference frame, as we can have several frames which can be used to localize objects. Let us first understand this problem in practice. Let us consider this simple example, a robot and a person. If we ask the question, what is the location of the robot and what is the location of the person in the word frame? Observe that we ask about the location with respect to the word frame. It is clear that the location of the robot is 3, 3 on the x-axis and 3 on the y-axis for the robot, and the location of the person is 9 on the x-axis and 6 on the y-axis. Now if we ask the question, what is the position of the person, but this time with respect to the robot? Such a question is relevant in real world, because usually a robot can localize a person using its camera or other sensors. So basically, the robot will determine the location of the robot with respect to itself. To respond to this question, we need to consider another reference frame, but this time it is attached to the robot. Look at the red frame. We call this frame the robot frame, and it is colored in red and attached to the robot in this slide. Now we can observe that the location of the person is 6 on the x-axis and 3.5 on the y-axis. So you can observe that the location has changed because the reference frame has also changed. Now combining both frames, we can observe that the location of the person is expressed as 9, 6 in the word frame and as 6, 3.5 in the robot frame. So it is important to note that the location of an object is dependent on the coordinate frame that is used as a reference. In real-world robotic applications, we typically have a robot that knows its location in the environment with respect to the word frame, and this robot would observe objects and can find their location with respect to itself, meaning the robot frame. So for example, in this example here, we have the robot that is located in 3, 3 in the word frame, and the person is located by the robot itself in the coordinate 6 and 3.5, but with respect to the coordinate frame of the robot, F robot. So the general localization problem is, what will be the location of the person in the word frame if the robot knows its location in the word frame and also knows the location of the person in the robot frame? Of course, in this simple scenario, we can manually determine this, but in general, we can determine the solution to this question by performing transformation between the coordinate frames. Let us understand this in the next lecture. In the previous lecture, you have learned how to express the position and orientation of a robot in a two-dimensional frame, which represents a fixed reference. This fixed reference is used to localize the robot in space. However, in real world, we noticed that we can have multiple frames and we may need to localize objects with respect to several frames. Recall our localization problem. A robot knows its global location in the world frame and knows the location of a person in its own frame. So the question is that the robot would like to estimate the global location of the observed person in the world frame. First, we need to understand what a transformation is. A transformation can be one of two possible types. A translation, which means a frame is translated by a certain vector with respect to another frame, and a rotation, which means a frame is rotated by a certain angle with respect to another frame. This is an example of a translation between frames W and W1. Observe the translation vector with a solid red line. It is the sum of two translations. One translation on the x-axis, the dashed red line on the x-axis, and one translation on the y-axis, the dashed red line on the y-axis. The sum of both is the resulting translation vector between frame FW and FW1. This means that the location of the robot in W1 will be shifted as compared to its location in W. This is an example of a rotation between two frames W and W2. Observe that the two frames are in the same origin. This means this is a pure rotation. There is no translation involved. The two frames are rotated by an angle theta. This means that the location of the robot in W2 will be affected by this rotation angle as compared to its location in W. The question is, what is the relation between the pose of the robot in W and the pose of the robot in W2 when W2 is rotated as compared with W? In a more general case, we can have a transformation that involves both translation and rotation, as illustrated in this slide. Basically, any transformation is a combination of a translation and a rotation. W3 is translated by a certain vector as compared to W, and also rotated by a certain angle. Again, the question is to find the general relation between the pose of the object in W and the pose of the object in W3. Let's look how can we determine this in the next lecture.